Hello and welcome to the AICE Chemistry lecture series. In this video, we're going to look at the final section of chapter 11 and the final section of the group 2 chapter, which is the reactions with water. Now, this title is a little misleading because we're going to see more than just the reactions with water here, but this is where we're going to start seeing the reactions of the group 2 metals and compounds with water, and then we'll move on from there. So let's get started. So, group 2 elements react with water to form basic hydroxides. Now, this is true of all of the group 2 elements, especially as they get more and more reactive. We can see here in the graphic that when a group 2 metal reacts with water, the products are twofold. We had the group 2 hydroxide, which has the general formula of MOH2, because the hydroxide ion is -1 and the metal is +2. And then H2, which is hydrogen gas. So whenever any of the more reactive group 2 metals react with water, this is always going to be the product, the hydroxide with hydrogen gas. And as a result, what we're going to see is bubbling. We're going to see with calcium, strontium, and barium, we are going to see very heavy bubbling of the metal. Now, as we go from calcium to barium, the bubbling will get more vigorous. The bubbling is hydrogen gas that's being created. And because the metals are more reactive, it gets more and more vigorous as we go down the group. Because the reactivity of the metals, like we have discussed earlier, also gets more reactive. The one compound here that is metal here that is going to be a bit different is magnesium. Magnesium does have a very unique interaction with water. And that's because depending on the conditions of the reaction, we can actually get two different processes to undergo. Whenever magnesium is reactive with cold liquid water, we will get that magnesium hydroxide that we will get with any of the other group 2 metals. So with cold water, magnesium undergoes the same reaction to create the hydroxide and hydrogen gas that the other metals do. This reaction is very slow, like we would expect, because it is the least reactive out of the metals that we usually talk about. Obviously, beryllium is a lot less reactive, but it's the least reactive of the ones that we normally talk about. So we'll get some bubbles. The solution will be basic, as they are with all of these, because of that the hydroxide that's being created. So we create basic solutions when these reactions happen. However, if we react magnesium with steam instead of water, now, the main difference here is that when we create steam, it's going to be gaseous water. So notice, same reactant, but different states of matter, liquid versus gaseous. Magnesium reacting with steam, with gaseous water, and we usually use this kind of setup where we heat up water, create the steam, and then pass it over the magnesium metal. It's going to create the hydrogen gas, but instead of reacting to create the hydroxide, we will get the oxide. It's going to glow a bright white color, just like it does when it reacts with oxygen, but it's going to form a solid magnesium oxide layer, very similar to the reaction with oxygen, but it's going to have the addition of also making hydrogen gas. So this doesn't happen with the other metals. Calcium, strontium, and barium are not going to create the oxide when reacted with steam. They will go and create the hydroxide just like normal. But because magnesium is less reactive than them, it undergoes a different reaction with steam than it does with water, with cold water. This is a perfect example of why conditions are important. Even though both of these have the exact same reactant, which is H2O, it reacts different with liquid water versus gaseous water. The gaseous versus liquid, the state of matter, is considered to be a condition. So whether the water is liquid or gaseous, for magnesium, not for the other group 2 metals, it will make a difference, creating magnesium hydroxide with the liquid cold water, but magnesium oxide with the hot gaseous steam, which is just water, of course. So that is something to keep in mind. This is because of that reactivity, the same reactivity we see going down the group, how it gets more reactive. Because of the low reactivity of magnesium, we see this difference. Now, I should also say that with magnesium hydroxide and calcium hydroxide, like we will discuss later on, magnesium and calcium hydroxide are only slightly soluble in water. So whereas with strontium barium hydroxide, the only observations are bubbles, with the magnesium and with the calcium, we might see a white precipitate or a white solid being created. Mainly with magnesium will definitely have that solid being created. With calcium, if there's enough calcium, it's concentrated enough, we'll also get a white solid. Or sometimes what we will say is that it will turn cloudy. It will turn cloudy as the solid starts to float around. You can see that solid, white solid here in the picture. But as that white solid, once enough calcium hydroxide is created, that calcium hydroxide being only slightly soluble in the water is going to cause a cloudy look to the solution. So it will turn cloudy as well as, or we're going to say there's a white solid being created. But that's only with magnesium and calcium. And that's because the hydroxides are going to become less soluble as we go down the group. More soluble as we go down the group. Meaning that magnesium hydroxide and calcium hydroxide are only slightly soluble, they're not heavily soluble. And we're gonna talk more about this solubility later on, because this does become a big deal. It's something that we're gonna see recurring throughout the whole section, where the state of matter of the products are going to depend on their solubility rules, on whether these products are soluble or not. Something that we need to start to learn and to memorize. But like I said, we're going to talk a little more about this as we go through this. So just for now, remember, magnesium hydroxide and calcium hydroxide are only slightly soluble in water, and so they might form a white solid or a precipitate when they're products. Or sorry, not precipitate, a cloudy look when they're products. Group 2 oxides will also react with water, just like the metals themselves, and the reaction is actually very similar. Group 2 oxides are going to give a very similar reaction when they react with water to create the hydroxide of the metal. The main difference here is that we're not going to see bubbles. There's no hydrogen gas being created. It's just a hydroxide. So for example, barium oxide will react with water to create barium hydroxide, which is aqueous because that is highly soluble in water. Because of the dissociation of the hydroxide ions, and this also happens with the metals when they react with water, the solutions we make are basic. For example, the barium hydroxide, as all group 2 hydroxides will do, will dissociate into barium and hydroxide ions. Those hydroxide ions are what make this solution basic. Because remember, hydroxide makes basic solutions, hydrogen ions make acidic solutions. So as we get more and more hydroxides, these solutions tend to get more basics. And that we can see in the solubility down the group. The solubility of the hydroxides increase down the group, meaning that as we go from magnesium hydroxide to calcium hydroxide to barium hydroxide, so on and so forth, we get more and more soluble oxides. So when magnesium oxide reacts with water, it creates magnesium hydroxide, which is only sparingly soluble. When calcium oxide reacts with water to make calcium hydroxide, that is partially soluble. It's a little more soluble. It's something we call lime water. And we'll talk more lime water at the end of this section. And then when barium hydroxide reacts, it creates barium oxide reacts, creates barium hydroxide, which is very soluble in water. As these become more soluble, more hydroxide ions are released. So as we go down the group, they become more soluble which equals more hydroxide ions in solution, more aqueous hydroxide ions. That means that not only are the group 2 hydroxides more soluble as we go down the group, the solutions become more basic. The basicity increases down the group. A solution of magnesium hydroxide, and these were what I will consider equal solutions, equal molarity solutions. The pH of a solution of magnesium hydroxide is only around 10, whereas for calcium hydroxide is between 11 and 12, and for barium hydroxide is between 13 and 14. They get more and more basic as we go down the group. Again, this is because of the hydroxides. The hydroxides are more soluble as we go down the group. They dissolve more, which leads to more hydroxide ions in solution. And the more hydroxide ions means that we have more basic solutions. So it's something to keep in mind. It's also what dictates whether we're going to have a solid being formed. Magnesium hydroxide is only sparingly soluble, which means we're going to see the formation of a solid in that reaction a lot more quickly as the solution very quickly becomes saturated. So it's very important to understand the solubility of the group 2 compounds, especially of hydroxides here, as we're talking about that discussion, because they're not only going to dictate the state of matter of the products, but also how basic the solution is. The more basic it becomes, there means that there are more hydroxides, which means it's more soluble. So from top to bottom, more soluble hydroxides, more basic solutions. Now, because the hydroxides are basic, because they have hydroxide ions in them, that also means that they're going to undergo neutralization reactions with dilute acids. And really with any acid, it doesn't need to be dilute, although we normally look at dilute acids as an example. But as we have a hydroxide ion in the group 2 hydroxides, those can react with any acid, which remember acids are going to have this HX structure where hydrogen is in the front and then we have some form of anion. So if we have something like nitric acid, for example, strontium hydroxide could react with nitric acid and the compounds that they create are always going to be the same. We're always going to get a salt, which in the case of the strontium hydroxide with nitric acid is going to be strontium hydroxide. The cation is going to come from the group 2 metal, and the anion, in this case the nitrate, is going to come from the acid. So here we have strontium hydroxide reacting with nitric acid, and it creates strontium nitrate as well as water. Water is always going to be the other product, as it always is in neutralization reactions. Now, one of the things that you need to be aware of, again, is the states of matter. The fact that this strontium hydroxide is aqueous and that the strontium nitrate is aqueous is due basically because of the solubility rules. We have learned about solubility rules in honors chemistry, but we also just discussed the solubility of hydroxides, or group 2 hydroxides. Strontium hydroxide is being pretty far down the group, is going to be aqueous in state of matter, and nitrate, which we haven't discussed yet, we will later, but nitrates are always aqueous, are always soluble. So these states of matter are always going to come from those solubility rules. Obviously, things like acids are always going to be aqueous because that's what makes them acids. Water is always going to be a liquid because it's always going to be water. But the ionic compounds, the strontium nitrate, strontium hydroxide, those come from the solubility rules. And it's important because where the reaction is always the same, the state of matter are not necessarily going to be the same. For example, when calcium hydroxide reacts with hydrochloric acid, we go from a probably cloudy solution, because calcium hydroxide we discussed is partially soluble, to a completely clear solution. Because when calcium hydroxide reacts with hydrochloric acid, it becomes calcium chloride. Let me write the reaction here really quick so everyone can see it. But when CaOH, when CaOH2 reacts with HCl, what we get is CaCl2 and water. Well, the CaCl2 here is aqueous because our chlorides are always aqueous. And again, we'll look at that solubility later on, but it's something you should remember from honors chemistry. And calcium hydroxide is partially soluble, so depending on the concentration, it could be solid as that cloudy solution that we talked about. So the cloudy lime water will turn clear when we have hydrochloric acid in it. On the other hand, if we're reacting magnesium hydroxide, which is completely solid, magnesium hydroxide is very fairly insoluble. When magnesium hydroxide reacts with something like sulfuric acid, H2SO4, what we get is magnesium sulfate, MgSO4, plus, again, water, which we always get. Well, magnesium hydroxide, we just said, is solid because it's usually insoluble. But the magnesium sulfate that's created is aqueous because magnesium sulfate is aqueous, whereas the heavier sulfates are not aqueous, they're solid. Because the solubility of the sulfates is going to be the opposite of that of the hydroxides. And again, we'll discuss the solubility of sulfates later on. But this is going to turn aqueous. So even though these are the exact same reactions, hydroxide of group 2 with an acid creates a salt and water. Hydroxide of group 2 with an acid creates salt and water. The state of matter of the hydroxide as well as state of matter of the salt, the ionic compound, are going to vary. So our observations are going to vary. The good thing is that we're never going to have to worry about colors. All group 2 compounds are, for the most part, except for a few exceptions, going to be white. But we do need to worry about whether we can see them or not. So that's the reaction of group 2 hydroxides with acids in these neutralization reactions that create water and an ionic salt. Again, what we need to worry about here is the state of matter of that salt and the state of matter of the hydroxide. Let's keep going here. Let's talk about group 2 carbonates. And this is another one, right? So group 2 carbonates have the general formula MCO3 because the carbonate ion has a -2 charge. And we already know that group 2 metals are always going to be +2. So it's a 1-to-1 ratio, MCO3. So we can have MgCO3, CaCO3, BaCO3, don't really matter. Now the carbonates of group 2 are all considered to be insoluble. So there's another solubility rule for you. Any carbonate of a group 2 metal is considered to be insoluble. There's no trend like with hydroxides where we saw that they became more soluble, or any trend like with sulfates where we saw that they became less soluble. With carbonates, it's just they're all insoluble. So they're all going to be these white solids that don't dissolve in water when we are looking at them. So keep that in mind, because whenever you have the state of matter for a group 2 carbonate, it's always going to be solid for those group 2 carbonates. So what reactions could do group 2 carbonates undergo? Well, group 2 carbonates react with acids as well. Just like group 2 hydroxides react with acids, group 2 carbonates also react with acids, but they do it in a bit of a different fashion. Group 2 carbonates are going to react with the acids to create a salt, again, so that same ionic compound, water, again, same ionic compound with water, and carbon dioxide. Now you have to be careful here. A lot of the time when we have these gases being created, like carbon dioxide here, we are going to see bubbles as an observation. The carbon dioxide being created and the fact we have an acid in the mix, which is aqueous, which is liquid, is going to mean that this carbon dioxide gas is going to be seen as bubbling or bubbles. Now, the state of matter for the salt, again, like we just discussed earlier, is going to be dictated by the acid. Why the acid? The salt is created so the anion, Mx, that X comes from the acid. So depending on what this acid is and what combination of group 2 metal with what anion we get, it's going to determine the state of matter of that ionic compound. So for example, barium carbonate with sulfuric acid. Barium carbonate reacts with sulfuric acid to make barium sulfate, water, and carbon dioxide. So if we grab some barium carbonate, we drop sulfuric acid on it, we're going to get a small amount of effervescence, so the carbon dioxide bubbles, as well as water, which we don't see, and the barium sulfate. Well, the barium sulfate is a solid. Remember, sulfates, group 2 sulfates, get less soluble down the group. So as we go from top to bottom, from magnesium all the way to barium, the sulfates are going to become less soluble. Oops. Meaning that something like barium sulfate all the way at the bottom is going to be completely solid. So this reaction, again, it's the same reaction as any of them undergo. The carbonate reacts with sulfuric acid and it creates the barium sulfate, the water, and the carbon dioxide. We see some bubbling at first, but then it's going to quickly stop. And that's because that carbonate is going to be covered with that solid precipitate, with that solid barium sulfate. So the barium sulfate is going to be solid. On the other hand, calcium carbonate, when it reacts with nitric acid, for example, will lead to complete bubbling and effervescence with no solid in place. That's because the nitrates of group 2 metals, and really any nitrate, is going to be soluble. And you know, this is a typo. It's going to be soluble. So the calcium nitrate that's created is aqueous. And so we don't get a solid here. The calcium carbonate reacts with the nitric acid to create calcium nitrate, which is aqueous, no solid, and we still get that carbon dioxide, so we get bubbling here. So we talked about solubility, and solubility is very important. So here's a bit of a cheat sheet when it comes to the solubility of group 2 compounds. Group 2 oxides and hydroxides are going to increase in solubility as we go down the group, meaning that things like magnesium hydroxide or magnesium oxide are going to be very sparingly soluble, so they're going to be solids most of the time. And then things like barium hydroxide, barium oxide, or strontium oxide and hydroxide are going to be very soluble as they're farther down the group, and so they're going to be aqueous. Chlorides and nitrates of group 2 metals are going to be completely soluble, so they're going to form clear solutions that are aqueous. Carbonates, on the other hand, are the exact opposite. They're all going to be insoluble, so they're going to create these white solids or precipitates. And then for sulfates, we have the exact opposite trend as for hydroxides. Group 2 sulfates are less soluble as we go down the group. They go from being aqueous at the top to being solid at the bottom. So something like magnesium sulfate will be aqueous, as we saw earlier, but barium sulfate is a solid. So this is just a little graphic that can help you remember the general solubility rules for the most common compounds we work with: sulfates, carbonates, nitrates, chlorides, and hydroxides and oxides for group 2 elements. Now, you do have to remember, these are solubility trends, solubility rules, meaning that in order for any of these to apply, there needs to be water involved. There needs to be some kind of aqueous solution. That is not always the case. One of the most common mistakes I see folks put is bubbling in something that does not have a aqueous solvent in it. So let's look at an example where water is not involved. So, thermal decomposition of group 2 carbonates. Group 2 carbonates undergo another reaction. Group 2 carbonates can thermally decompose. That means that when they're heated, that's what the thermal part is, they decompose, undergo a decomposition reaction, breaking apart. So the reaction of group 2 carbonates being heated is going to lead to the group 2 oxide being created and carbon dioxide. So we get that group 2 oxide, so whatever the group 2 oxide is, magnesium oxide, calcium oxide, strontium oxide, and the carbon dioxide. Now, a common mistake that I see here for students is that they see carbon dioxide gas and they're like, oh, there's bubbling because there's a gas. Well, there's no bubbling here. Why? The reactant is a solid. We're heating a solid. The products are a solid and a gas. There is no liquid, there's no water, there's no aqueous solution here. And so there can't be bubbles. Yes, there is a gas being created, but carbon dioxide is a transparent gas. We don't see it. And so there is no bubbling here because there is no aqueous solution or water involved. Now, what we can talk about this with this reaction, apart from just what are the products, which are the oxide and the carbon dioxide, is thermal stability. And again, the word thermal just means heat, and then stability means how stable it is. So when we talk about thermal stability, we mean how stable are these compounds when exposed to heat. The higher the thermal stability is, the higher the temperature they will need to decompose, or to start decomposing. Not every carbonate is built the same way. Magnesium carbonate decomposes at very low temperatures because it's very thermally unstable. But barium carbonate decomposes at much higher temperatures because it's thermally more stable. In general, the trend is that as we go down the group on group 2, the elements get more thermally stable. Thermal stability increases, meaning that the temperature that we need to break down that compound is going to increase. So we're going to need higher and higher temperatures for these reactions to happen. Now, thermal stability increases on the group. This is why things like calcium carbonate, or what we normally call limestone, doesn't just start breaking apart the minute that it's exposed to any kind of heat. So for group 2 carbonates, when they decompose when exposed to heat, they turn to the metal oxide and carbon dioxide. There is no bubbling because there is no water or aqueous solutions. And the thermal stability of the group 2 carbonates is going to increase down the group, meaning that they will need higher and higher temperatures in order to break apart or to start decomposing. Now, group 2 nitrates undergo a very similar reaction. The thermal stability of group 2 nitrates is exactly the same as that of group 2 carbonates. As we go down the group, the thermal stability of the group 2 nitrates increases, meaning it takes higher and higher temperatures for those compounds to start to decompose. The main difference is that when we heat the nitrate, which is nitrate is NO3 minus, so we have a 1:2 ratio between the group 2 metal and the nitrate. They undergo a very similar decomposition reaction where they create the metal oxide, but instead of carbon dioxide, they create nitrogen dioxide, and additionally to that, they will create oxygen gas. So we get 2 gases here instead of 1, so we have 3 products in total. Again, there is no bubbling here because there is no aqueous solutions or liquid. But this does actually give us an observation. Nitrogen dioxide is a toxic brown gas. And so where we can see the oxygen being created, we can see the nitrogen dioxide being created. And that's going to look like a toxic brown gas. So we will get an observation of a brown gas when a nitrate, a group 2 nitrate, is decomposed. Here's the reactions, right? When we decompose magnesium nitrate, what we get is magnesium oxide, nitrogen dioxide, and oxygen. When we decompose calcium nitrate, we get calcium oxide, nitrogen dioxide, and oxygen. Strontium nitrate, SRO, NO2, and 1/2 O2. So you can see how as we go down the group, because these are more reactive, we get more brown gas. It's, because the reaction happens faster. The amount is actually the same because the ratios are the same. But it happens faster, so we get more at a time. And so we see that NO2, that's going to be that brown gas that gets created. So that's the decomposition of both group 2 nitrates and carbonates. It's very similar. The trend in thermal stability is the same. As we go down, they require higher and higher temperatures to break down because they're more thermally stable. You do not need to know why this happens. We will go into why they become more thermally stable in A-level chemistry in chapter 19. But for AICE chemistry, you just need to know the trend, not why the trend happens. And you need to know that for the carbon group 2 nitrates, we're going to get a brown gas as an observation of the decomposition, but not for the carbonates. For the carbonates, we don't actually have any kind of observation because the carbon dioxide that's created is transparent. So we wouldn't actually see it here. But the nitrate does. The nitrate gives us a brown gas. So this is a perfect transition to talk about gases, right? Because we said that the nitrate decomposition gives us a brown gas, but the carbon dioxide that's created in the decomposition of the carbonates, we can't see. There's no actual visual cue here that any reaction's actually going on. So what exactly do we do in the lab when we don't have a visual observation of a gas that identifies it? Because if we see a brown gas, we know it's nitrogen dioxide. But what if we just see bubbling? Or we don't even see the gas, but we know that there's a gas being created? How do we test for it? Well, there are 4 tests for 4 common gases that we can carry out in the lab. And these are going to be essential for your paper 3 qualitative lab. So there are 4 ways in which we can test for different gases. If we know there's a gas being created, or we suspect a gas is being created, we can test that gas for its to identify it, to figure out what it is, in 3 ways. The first 2 tests involve a splint or some kind of wood. With hydrogen gas is flammable. So if you have hydrogen gas being collected, or you suspect you have hydrogen gas being collected, the test that you can make to figure out if it is hydrogen gas is to collect that gas in a test tube and then grab a wooden splint that has been lit on fire and hold it near the test tube. If you hear a pop, that's the hydrogen gas being combusted. That is a positive test for hydrogen gas. So if that gas pops a lit splint and you hear that sound, that popping sound, you will get that means that you have a positive test for hydrogen gas. On the other hand, that doesn't work. You can blow out the wooden splint. And by blowing out the wooden splint, you'll end up with this glowing splint where it's not quite out, but there's no fire. If you put that splint into your test tube of gas and that splint either glows more brightly or fully reignites, that is a positive test for oxygen gas. So if that happens, you know you had oxygen gas. Ammonia is another gas that can be created during chemical reactions, NH3. Ammonia gas is basic in nature, alkaline in nature. That means that if we have a piece of red litmus paper and we wet it and we hold it up to that gas and it turns blue, that is a positive test for ammonia gas. And that's because ammonia gas, again, is basic in nature, so it turns a red litmus paper blue. The water needs to be there so that the ammonia gas can be trapped in the paper and actually react with it. And finally is the carbon dioxide test. And the carbon dioxide test is what we started talking about, right? We have the carbon dioxide being created in the decomposition of the carbonates, but we have no visual indication that it's actually happening. So how do we test for it? One of the ways to test carbon dioxide is to grab a tube into the reaction, try to seal off the entrance of the test tube, and then get that gas to go into a test tube that is full of lime water. Now, what exactly is lime water? Lime water is the common name for calcium hydroxide, CaOH2. So lime water is a solution of calcium hydroxide that is very highly saturated. So it has holding all the calcium hydroxide it can possibly have. When we put carbon dioxide gas into calcium hydroxide solution, that carbon dioxide will react with the calcium hydroxide, and you don't need to know the reaction right now, but they will react together, and that solution will turn cloudy or milky. So if we get the gas and we get it into and bubble it through a solution of calcium hydroxide, otherwise known as lime water, If it turns milky, that's a positive test for the carbon dioxide, because carbon dioxide will react with calcium hydroxide and turn milky. And that milkiness is just a precipitate that's created, a white precipitate that floats around the solution. And that's it. These are the 4 tests for gases. Anytime you are suspect a gas is being created during a lab in your qualitative part of paper 3, or you know there's a gas being created, you are supposed to use these 4 tests to identify what the gas is. So you can't just say there's bubbling. You need to identify what the bubbling is for. So you will say it's bubbling, and then run these 4 tests to figure out which of the 4 common gases it is. All right. That's it for chapter 11. I will see you all in the chapter 12 videos. Thank you for watching.